that will include whatever is covered until today with problem from assignment 4 and 5. Right? And then we will continue with the rest of the course for the next 2 classes, and there will be somebody waiting. Which will not be included in quiz 2. So whatever we cover the assignment problems will definitely be there for quiz 2, including whatever we have covered after quiz 1. So we looked at the problem for the rotational, or rather flow between cylinders or spheres. We wrote the general expression for the. So here, what we are assuming is that the cylinders are spheres. So the flow between 2 cylinders or between 2 spheres. The flow is only the angular region between the cylinders or spheres. So the cylinder, this would be the both cylinder and sphere. This is true, is what we assume. Now the flow between concentric spheres, we showed that actually phi is given by C1r is C2 by r squared times sin theta. When comparing with what we had for the cylinder, which was probably C1r C rather plus C2 by RC. So here is different because it's a dependence on theta as well. And to determine the constant C1 and C2, I pointed out that the boundary conditions would be omega I times kr times sin theta that would have to be taken into account. Right? Because for the tangential velocity would also include the sin theta term. So this would be omega naught r sin theta. So if you put the two together, what you would get is d phi to be formula given in Stewart Lightfoot can be obtained. Easily verify that the boundary conditions are satisfied, or we might have that easy to verify. So you can put R into the kappa times R and then verify if you recover that, the first condition, and then so this is the formula. I mean, it's given in the textbook in the exercise section, so you can easily verify that this profile satisfies the boundary condition. Now, one of the important points in this, as I said, is in these problems, is when you have flow out of a cylinder or a sphere, we need to be able to calculate the flow rate. Here, because the fluid is rotating inside the space between the cylinder and the sphere, the important quantity is what is called as the torque acting on the cylinder or sphere. If you look at the text, in fact page 91, where the words would give a formula for the torque, there actually the inner cylinder is not rotating, and page 91, I'm going to just write down the formula, and although the formula is very simple, to derive it actually will take some time. Actually, the torque is actually given by, we gave it down to the torque in the contact force, P x cross P dA. This is the general formula. So, what he writes in the textbook, I'm just going to write, if we have time to discuss it, this will not be required at this stage. We'll take it up, we don't have the time to go into it in detail. But it's possible for you to derive this. But what he has here, the cylinders is he writes the following formula between 0 to L, where we're talking about a particular length of the cylinder, right? And then integral is also phi and converted to the notation that we have. This will be T RC phi times RC. Evaluated at RC, he is calculating actually the torque on the inner cylinder there. And then times KR d phi dz. So everything is the R, that this is an integral of phi and z. So the R is actually, if you're calculating on the inner cylinder, it would be RC equal to kappa times R. You can also calculate the torque on the outer cylinder. That would be RC equal to capital R. And if you now the ERC can be easily shown to be here. ERC phi is Q times DE phi by RC minus D phi by RC. Unfortunately, I don't have the formula for the theta would be very similar. So first of all, given this formula, it should be very easy for you to derive the result, right? So the velocity profile for the cylinder is actually d phi is equal to omega I kappa square minus omega naught. Here is a function of 12 times RC plus evaluated at RC to kappa times R. Obviously, this RC also converted to kappa times R. So this is all calculated the surface of the inner cylinder. That's what you have to understand. Right? How do you get this formula? Right? This formula is obtained from here. It's a long-winded procedure. Although the formula finally looks very simple, you will find that the formula for the general formula for the torque is actually quite complicated. So first you have to express x in terms of cylindrical coordinate. T has to be calculated or expressed in terms of the stress tensor, which is n dot t. Now what would be n here? We are calculating on the surface of the cylinder. N would be ERC. So the sign is important for inner cylinder. I think will be coming out of the inner cylinder. So N would give you ERC, and I have to calculate N dot with tau. And then I calculate the cross product of x with that. The x also expressed in terms of the cylindrical coordinate. Right? Now x in terms of the cylindrical coordinate would simply be, first you should know how to express it in terms of the Cartesian coordinate. What we want, everything we want expressed in terms of the cylindrical coordinate. So you see very easy to show that this is simply replaced by this will simply become RC times ERC possibly, right? So there will be no dependence on phi, right? So that is the point. I mean, this is the point on the xy plane, on the x1, x2 plane. That point can simply be expressed as RC times ERC. Right? So you have to figure that out. I mean, I don't remember. And then you have to take the cross product of that with this. Right? And then everything will depend on ERC and E phi. Right? And EZ. Those will all come into it. Because you have to express the cross product of two vectors in cylindrical coordinates. We already have the formula. Right? So I put a question mark on this, and then, but what we want are the components. See, this is simply the Z component, or what we call the Z component, or the X3 component, or the Z component of the torque. You will actually find for this special problem that X and Y components are actually zero. Even the words we write this as the Z component, which is correct, but actually there are no other components for this problem. So in general, you will get both the X, Y and Z, right? So what you would actually have to do is that since the ERC, E phi are also functions of phi, and you can't just have something, finally you want to convert everything back to the Cartesian coordinates. So if you want a component along the X, Y and Z, you will have to reconvert, and you will actually find that because there is no phi dependence on this, right? So none of the stress components would have any phi dependence. So you have a cos phi and sin phi coming. The integral 0 to 2 pi of those would be 0 for the X and Y component. That is why X and Y components vanish, and you will get this for the Z component, right? So this is what we will get, and the final answer is 4 pi torque Z component is equal to 4 pi that this matches with the formula given on page 91, except that he doesn't have the omega I, because there the inner cylinder is actually not rotating. Because of the motion of the fluid, which is induced by the motion of the outer cylinder, there would be a torque still on the inner cylinder. Right? You can similarly calculate the torque on the outer cylinder by simply doing everything at RC equal to R. Otherwise, the integral remains the same. Right? So you can try that, you will find that the torque on the outer cylinder would be the negative of this. Right? So the formula and the procedure leading from this to this is quite complicated. You can try to derive it, but we first take up when we come to calculating the force, which is easier to do because torque of it requires a cross product. We can sometimes we take a more detailed view of the torque. The formulas, even though the final formula is quite simple, it's the general calculation of torque in cylindrical or spherical coordinates, or even for that matter in Cartesian coordinates, is quite difficult.
Sir, can we find torque by another formula, which is we have got d by drc rc v phi. Tr phi is dv phi by drc. So can we find it out by that formula?
Yeah, that is what we have to use finally. Right? That's what you have to use. General formula for torque is this. That's what I told you to. You can try deriving, what you will get. In the general case, what would this be? This would in fact involve all x, y and z components. You can calculate the general formula. You have all the elements to calculate. I am outlining the procedure. You have to express this in terms of cylindrical coordinates. That's very easy to do because simply x1, x2. We know how e1, e2 and e3 are dependent on the cylindrical coordinates. But E3 is just a Z, you make the same, so you can easily get that. Right? So put all that in. Take the cross product. Now T would be n dot T, as expressed in cylindrical coordinate. Right? That is PR, CRC, DRC, phi, and so on. Now we take the dot product n given by ERC. So you will really find that the first row of the stress component would only come in. That would be the vector T. On top of that, you have to now take the cross product of these two, right? And then you will get terms involving ERC, E phi, and EZ in general. So the ERC, E phi have to be again converted to E1 and E2. So finally, because those are coordinates which are varying with those are units which are varying with the position. Whenever we talk about the overall force of torque, we don't express it in terms of the cylindrical coordinates. It has to be expressed in terms of the Cartesian coordinates alone, which are fixed in space. Right? We have to convert the ERC, E phi to EX, EY, or E1, E2, and finally, right, you have to substitute. If you stop there, you get the general result. Right? But if you want to specialize to this, where only the V phi component is present, and top of it dependent on RC alone, then you will find that the X and Y components will simply vanish. Right? And then you will get this for the Z component. Right? If you want, if you try to carry out the derivation, but it will require quite a bit of steps before you get to this. The only point I need to make that this formula which appears in virtually everyone may be quite obvious for them, but it is certainly not obvious to me how you get that formula. So I'll leave it at that. The calculation of torque is of practical importance. We'll see in a later case where it is actually used in a viscometer to measure viscosity. Are there any questions on this? So this concerns rotational flow. There is another interesting problem involving the flow between two spheres, and there we get d theta rather than d phi as the only component. So you talk about a highly viscous fluid flowing between two spheres, and that is problem number 3. Very viscous means the inertial terms can be neglected. That is what is called as creeping flow in comparison to the
light I want.
Light?
This light.
Okay, can you switch on? Thanks. So the creeping flow consists of a sphere, two spheres actually, and the fluid is flowing out of into the region. So let's say this is the origin of the sphere, and we call this as the z-axis. So this is kappa times r. This is r. The fluid comes in and flows all along and then goes out of the sphere. So here the flow is, you can sort of see that it is along the theta direction, and so you are asked to assume that this is the only component that is of relevance. That's an approximation. It is still a one-dimensional flow. Here V is the theta. Right? So what does the continuity equation say? Now you can easily verify. Right? The continuity equation actually says that d by d theta now d theta alone not, but d theta sine theta is actually 0. And so d theta sine theta is some function of r and phi. What you are asked to do is to neglect this dependence on phi, and so that we get d theta sine theta is some function of r alone, which we will get u of r. Right? So I'm going to go through the steps quite quickly. Right? Again, you'll see that dr will turn out to be, we have already calculated this, and d theta will be d sine theta, and d phi will be dr minus d cos theta. That will hold true. And so if you substitute this into the equation of motion, you will get that the pressure would be given to be minus rho g r cos theta plus some function of theta. Here, in fact, you would find that the equation of motion tells you that you don't have to neglect dp by d phi, but it would automatically turn out to be 0, because the body force component in the phi direction is 0. You will verify, you can easily verify that all the viscous terms, right, in the phi component of the equation of motion will also vanish. So you get dp by d phi to be 0. That, of course, assumption we don't have to make. So we will get dp to be a function of r and theta. We integrate the r component of the equation of motion, you will get this. Right? You will get this. Once you have verified from the phi component that dp by d phi is actually 0, so you can easily verify that this is just coming out of the integration of this. You get dp by dr, and you integrate this, you get gr cos theta times rho. Right? So that's very easy to verify. The crucial equation then becomes the inertial, the equation of motion in the theta direction. That would be minus 1 over r dp by d theta plus the viscosity times 1 over r square d by dr of r square dv theta by dr is equal to 0. Now what we have to do, we already know what dp by d theta is, right? So what I need to do is I calculate dp by d theta. dp by d theta is simply rho g r sin theta plus f prime of theta, and then I have to substitute for d theta here. So here if I substitute d theta is equal to u of r by sin theta. That formula is dictated by a continuity equation. Of course, we are neglecting the dependence on phi. That's an assumption you are asked to make. Right? So if you substitute it, what you will get is, I'll let you do all the intermediate steps. You should get this. So I leave all the intermediate steps for you to do. Right? So this would be important. You just have to substitute and do the manipulation. You should get this. Now I can clearly see this is a function of r alone. This is a function of theta alone. So I can make this to be some constant which I will call as c. Now I can solve for u independent of, not quite independent of this, but because c would have to be determined. So I can solve for this. That's very easy to solve. And what you would get is that. So how do you solve for that? So this would be, you can solve it here. Equal to c. So I can bring this over here. So this would be r by, so which would mean that r squared du by dr is c by r squared by 2 plus some constant, let's say c1, right? And then now dividing by r squared, I would get now I have to integrate it again, right? So this would be u would be given by cr by minus c1 by r plus c2. So what are the boundary conditions? I have three constants actually, right? One is c. We are not going to solve the determinant by boundary conditions on u, right? But how do you determine what are the boundary conditions? So the spheres are stationary. So the solid boundary, what are the boundaries here? The boundary is one on the surface of the inner sphere, one on the inside of the outer sphere, right? So what are the boundary conditions? You can clearly apply the no slip conditions. U would be 0 and equal to 0. So you substitute that, you can easily determine C1 and C2, right? So 0 is and 0 is also equal R by 2 minus C1 by R. also vanishing. So I think we can't really say anything. I think there should be an R here. And anyway, we'll verify that. So certainly this satisfies both the boundaries. Form is really one which is a function of R and another which is the inverse of R. Plus we have a certain constant term, right? So now how to find the C? The C is very analogous to what we have in the flow down the cylinder, where the constant is determined in terms of pressure difference between 2 points. That's exactly what the formula given implies. So what for that I need to solve this. I have to solve this. Now you see this is the first order equation in F, right? So if you integrate this, you will get another constant, right? And on top of it, you have C. So you can see that you need 2 boundary conditions on F, right? And let's integrate this. So F prime of theta is C by sine theta. And so what is F of theta? F of theta is equal to, now the integral of 1 over sine theta turns out to be the logarithm of tan theta by 2. It's actually logarithm of mod tan theta by 2, right? Plus some constant, let's call it some constant A. So what the formula for virtual implies is actually what is calculating are actually the F here is F this. I'm just trying to establish between the notation given in virtual length. This is actually the modified pressure. Virtual length you will see you never express any relation to pressure, but always a modified pressure constant because of gravity or some other effect. Right? So this is what the modified pressure of virtual length would be. So what the formula implies is that it requires calculating the modified pressure at 2 points, one at this edge, right, which would mean that theta is equal to epsilon according to the figure you can see, right? According to the figure, that angle, the angle is given to be 2 times epsilon. So this is epsilon, and then we also would require the F or the modified pressure to be known at this. And what is the theta from this point? Theta for that point, right? So if you do the full circle, you would come to pi. So this would be pi minus epsilon. This is also epsilon, right? But you are measuring it from this, right? The z-axis, the positive z-axis. So theta is measured like this. So this angle is psi by epsilon rather, and this would be pi minus epsilon. So those are the 2 points at which F is to be known. Pi minus 2 epsilon. Pi minus epsilon only. This is only epsilon. Another here I am saying, not here, pi plus epsilon. This is pi minus epsilon, right? Maybe my figure is not clear, but if you look at this figure, you can easily figure out. So F1 is logarithm of tan epsilon by 2 plus A. So what happened to C? C is here. And F2 is C times log tan pi minus epsilon by 2 plus A. So clearly by subtracting these two, you get that C is actually equal to F1 minus F2, right? Divided by log mod tan epsilon by 2, that is log pi minus epsilon by 2, and you should be able to verify that this can be actually shown to be equal to f2 minus f1 by 2 logarithm of the cotangent epsilon by 2. Tan of pi by 2 minus epsilon is probably cot of epsilon. Tan of pi by 2 minus epsilon by 2 will be cotangent. So actually you can either express both in terms of the cotangent or in terms of the tangent, and so the effect of the modulus I think will get lost when you get the same product of two terms. And so what you will get is this. So I will get you to verify this, right? So finally you can express the, so this to get the answer of Birch relation, you need to only replace the f by the modified pressure. You get the answer given in Birch Lightfoot. This sort of completes the problem of calculating the velocity profile. The velocity profile is here expressed in terms of c, and that would have to be expressed now in terms of the pressure difference between the 2 points, right? So that is what we have, and then there's another question also here. Since there is fluid coming in, there is fluid flowing out, right? We also can calculate the mass flow rate, right? So mass flow rate is easily calculated once the velocity is known, right? So the general formula for the mass flow rate is integral rho b dotted with n dA, right? So now there is incompressible fluid, so rho is fixed, and v is here d theta, e theta. The n is also going to be e theta because it's actually flowing across a constant theta surface. That's the normal, right? In the direction, because it's flowing along the theta coordinate line. So the normal for the area element would be the normal to the theta equal to constant surface. You can have to think about it. That is what it would be. And then what would be dA? So dA would clearly have dr, d phi, right? And then what would be the metric coefficient would be r sine theta, dr, d phi. That's what you would get. Right? Now what are the limits of integration? The limits of integration, this is u, so the sin theta will actually get cancelled out. I mean, there's something you have to think about what is happening here, because after all this integral is it seems to be dependent on sin theta. So in principle it depends on where you calculate the flow rate. But however, the fact that d theta is inversely proportional to sin theta will make the whole integral independent of sin theta, so it doesn't matter at what particular angle. So this is some theta, right? At what angle you calculate this flow rate, in general it might depend, but in this particular case it doesn't matter, because the sin theta here is going to get cancelled with the d theta, which is inversely proportional to sin theta. So you can easily calculate the phi would obviously vary from 0 to 2 pi. What would be the? It would be kr to r. So you can easily get the final result. The answer is pi rho. And this is another. Get you do the integral and get the result. That is the final result. Are there any questions? Right, so you can complete the calculation, right, of the integral. We'll then go to the next problem in assignment 4, which is somewhat different. It will actually involve a radial flow. These problems are a good collection of one-dimensional flow problems, and we exhaust possibly all the radial flow we haven't seen in spherical polar. But if you look at the next problem in the assignment 4, it's radial flow between two circular discs. So I have one circular disc, right, and then another circular disc, and then the fluid is coming in here and flowing out radially. Again, you have to assume creeping flow. So this is the case in cylindrical coordinate. We have now very much exhausted all three possibilities of one-dimensional flow. Seeing flow down a circular tube would be Bz, is the only component. Seeing fluid between two cylinders and rotated, predominantly it is V5 that would be dominating, right? And here you are asked to assume that the fluid is coming here, right? It's a creeping flow, radial flow outward between the space between the discs, right? So fluid is coming in here and then going out. And again, there are a lot of assumptions that are not there in the problem statement, and even though I modified the problem statement, I still haven't given, so that's why I'm sort of discussing this. So now the continuity equation would be is equal to 0. So what this means is that RC times VRC is a function of phi and z. Again, you have to really solve the problem. To get to the answer, you have to neglect the dependence on phi. Right? So if you do that, then what you will find in this case, that with these approximations, the inertial terms would identically vanish in this particular case. So not in all one-dimensional flows, in the Cartesian coordinate would the inertial terms identically vanish. It seems that that's the case in the Cartesian coordinate, but this will not be the case. And so if you work through the equations, then what you will get is the answer that is given, right? What you should get is minus dP by dRC plus equal to 0. So this is what I call as U of Z. So now the question is, how do we solve the equation, right? So clearly V will be a function of RC alone and U is a function of Z alone. So I can rewrite this as mu d squared U by dz squared is equal to RC dP by dRC. Now of course the question is, what is P here? Right? P is actually P plus rho G Z. So according to the notation, you can clearly see that the origin here is the center point between the two plates. So the z-axis is what I have to fix, right? So this corresponds to z equal to plus b, and the bottom plate corresponds to z equal to minus b. Right? So clearly now this is a constant. You can easily prove that B plus rho times D times Z is a function of RC alone. That's what I'm calling as the modified pressure. So this can be very easily solved. Right? This is simply a mu times d squared U by dz squared. Right? It's a constant. So very similar approach. Right? This is simply going to give two integrations. It's going to give actually second order. It's a linear, it's a second order term, and Z would come in. If I integrate once, I'll get C1 times Z. Integrate a second time, I'll get the Z squared term also. If I put in the boundary conditions are, since both the plates are stationary, you would get that equal to B is equal to U at Z equal to minus B equal to Z. Right? So if you put all that, you will get the answer where U is actually RC times BRC. So BRC is what I want. So BRC would turn out to be P1 minus P2. So P1 and P2 are pressures. I guess at R equal to R1, because this is the R1. And so this is a centered line. This is a cylinder through which it is coming. So this is R1, and this outer distance is actually R2 that you can clearly see in the figure. So P1 and P2 are probably the pressures at R equal to R1, R equal to R2, actually RC should be at P equal to R1 and RC equal to R2. The final result is be a parabolic profile with Z. That's what you will get. So again, you can calculate the mass flow rate, right? So mass flow rate. So I'm leaving all these calculations for you to complete. Mass flow rate again is the same formula. So V is clearly ERC, ERC. And conveniently, the fluid is flowing radially outward, right? So it's flowing outward here, right? So that is actually corresponding constant R surface. Again, here you will find that the RC would drop out of the expression. So this is VRC times ERC. The normal is also ERC, and dA would simply be RC d phi dz. Phi varying from again 0 to 2 pi and Z varying between minus B to B. So if you substitute this, you will get this is given by B cube dependence on the mass flow rate. Mass flow rate has a dependence, cube dependence on B. Right? So this is what you will get. I'm giving all the answers rather than giving them on a separate sheet so that you can go and work this out and calculate these integrals and solve these differential equations and verify these answers. Are there any questions? Right? So this sort of completes the discussion of one-dimensional flows in assignment 4. Now we go to assignment 5. These are somewhat modifications of the problems we've already seen. We take the first problem in assignment 5. It's actually flow through a triangular duct. We have already seen flow through a rectangular flow between two plates. We have seen, for instance, that is flow through a rectangular channel because the space through which the fluid flows is a rectangular cross section it has. Now you are asked to consider a triangle. I just draw the cross section here. The notation will be slightly different. So we consider the flow. If you recall the what we considered for the flow between two parallel plates that flow through a rectangular channel, right? The flow direction was Z, and we saw that this axis we took to be X, and the one involving the width of the channel was Y. But now to follow the rotation in Birdsford Lightfoot, we have to modify it. If you want to recover the same formula in Birdsford Lightfoot for this problem, you will get, we make this Y and the width, the direction corresponding to the width, be X, but not only that, I just plot the cross section here.